Okay, so now we'll say where we reach. Okay. How many of you know recall merge sort? Do you remember recall merge sort? Yes, no. How many of you have seen merge sort? Okay, wow. Huh? It's like पहले हाथ ऊपर कर दो. अच्छा ठीक है, okay. So can you tell me the recurrence? So what do we do merge sort? Like basically we have a problem. We make them into two equal half, solve them and merge them. So what the recurrence we write? Plus what? And what does this solve to? Do you remember master theorem, Vaishali? Isn't the direct application of master theorem will work here? This is exactly what my point is. You should never remember any. I don't even know what master theorem is. It is just to scare people. Okay. So, no, this will come. We'll see. I didn't write it like for no reason. It will show up somewhere. Okay. Thus, for fun, we did some recurrences. Like it should look like an algorithm course, no? So some recurrences. Okay. I want to solve maximum independent set. You know what is maximum independent set is? Right? Input is G, output maximum size independent set. You could also have weight, then we will ask for maximum weight independent set. Okay. So do you know any algorithm for this problem? To find a maximum weight independent set. Any algorithm. What will you do? So what is a brute force? Excellent. We'll come to that algorithm. So what could be the potential the running time of this algorithm? Order? Which is same as I could have enumerated all subsets and checked whether it forms an independent set or not and pick the one with the maximum size. Agreed? Excellent. I could have also done so, but let's keep that thought in the head. Okay, the thought process you had is that if x goes into the solution, n of x does not go into the solution. Okay, so this is the thought process. Exercise, and I will ask you tomorrow. Don't tell me that I don't know. Give me an algorithm with running time 2 power. Okay, roughly 1.39 to the power n algorithm. You can take Asimov's polynomial as you wish. I mean, like, so this is the running time of algorithm I want. Exercise. Hint I have taught in the class. Okay, but I have a path. Okay, and say V1 to Vn. I have a path. Do you know how to find an independent set of this graph? Path. What? Okay, that's the one. Okay. So I said take this, take this. So always it starts from here and you can pick this up. Excellent. See, very smart. How much time did it take? Linear. Okay, good. Now I also have weights. What will I do? Look, if you have seen something, there is no point because then it doesn't help, right? Why? You were trying to do some greedily, right? Pick this vertex and pick the next vertex, pick the next vertex. Why did that not work? Hmm?
We are looking for max weight or max size.
Max weight. Yes.
So that will greedy approach will not work there because that does not achieve.
Can you come with a counterexample to your greedy choices? Everybody is like so keen on doing dynamic programming. Everybody is so keen on doing dynamic programming, and I'm not keen on doing dynamic programming. I want to do divide and conquer. I want to do divide and conquer. Enough here. Enough of this div. Enough of this. Enough of this. I want a polynomial time algorithm using divide and conquer. I don't want to do a dynamic programming. Now what will you do? Meri marzi. I want to do divide and conquer. Like exactly like merge sort. I want to do merge sort. What should I do? हट जाता हूँ कैमरा के सामने से. अब दिमाग में काम कर रहे लोग. ना घूमेगा वो. मैंने कहा अब दिमाग में काम कर रहे लोग. So I want divide and conquer. I do not like dynamic programming. I mean, seriously. No? All of you say dynamic programming because you all have seen it.
Divide and conquer also we can modify the merge step to complete.
You can consider in two cases. Take the middle element. Either it goes into the solution or it doesn't go into the solution. If it goes into the solution,
Perfect. Perfect. Maybe you should be sitting alternate. It was a joke. Okay. So Komal had a suggestion, and she says, let's pick up the middle vertex. Okay. So let's pick up the middle vertex. You want middle vertex, then I pick middle vertex. Vn by 2. And she says, she just wants to do what you said just here. Here. See, Sukanya, here. So she says, two cases. Either Vn by 2 is in my solution, or Vn by 2 is not in my solution. If Vn by 2 is in her solution, what she will do, then she will delete these guys, right? If this is in the solution, then clearly these guys cannot be in the solution. Finds a solution to this part, finds a solution to this part, and returns. right? So if I had, suppose, let's write a recursive algorithm, right? Just the way the merge sort is a recursive algorithm, let's write and conquer. Is it correct spelling? MIS or DCMIS. Oh, this sounds much better. Divide and conquer. MIS, like ACDC. It takes a graph G, that's it. Okay? What it does, I don't know. But it outputs max weights independent set. Okay? So it takes G and W, which is the weight function of the vertices, max weight independent set. Okay? So this is what it does. So what Komal says is that let's do one thing. Either Vn by 2 in the solution, then you return weight. So basically we are going to return max of the following thing. W Vn by 2 plus I have called DCMIS on whom? G minus closed neighborhood of V2, Vn by 2, right? And some weight function. I'm not writing this. Or I'm going to call DCMIS on what? G minus Vn by 2. Am I right? This is what I'm going to do. This is my recursive function, right? This is exactly what she asked me to do, right? Right? So for this G is a path, right? So let Vn by 2 be the middle vertex, and then I do this, okay? And here, if vertex set of G is equal to 2, find max weight, return. I wrote down code, right? I literally, if you can put this in C or C++, it will run. Is this a correct algorithm? Yeah, it's a correct algorithm, right? I mean, it's just a branching algorithm. What's the running time of this branching algorithm? Right, I branched, right? What's the running time of this branching algorithm? It's same as merge sort. Vaishali, I wrote an algorithm. All I'm asking you, can you write down the recurrence for this? I'm not asking anything else, right? I have written down an algorithm and I'm asking, can you write a recurrence for this? So what's the recurrence for this? हाँ? तू तो पीसी का कोर्स करके आया है ना? Yes, Vaishali. Would you like to contribute something? So tell me, I'll write down whatever you say. You want to pass writing this recurrence? Who is courageous to write this recurrence? Please, not all of you people. You want to try? You will learn. Trust me. You will learn. Trust me. If you'll try, you will learn. And never forget again in life. Okay? Don't think anything. Just follow the algorithm. This is it. Okay? So T of n less than equal to, it's a path. So in one branch, Vn by 2 is not in the solution. So you deleted this guy, and this guy. So how many vertices are there in the graph left? Okay, so should I write here n minus 3 plus t, another one is just n minus 1. Excellent. So this is definitely a correct recurrence. Okay, but just solve this recurrence. This will solve to this, I think, or even worse. Or worse, no, 1.45. This will solve to 1.45 to the power n. There is something we are missing here. What are we missing here? Wait. When you were writing this recurrence, what did you write? I didn't write it just for the sake of writing it. I wrote it because, what did you write? Why did you write? Everybody, all of you said to me, 2Tn by 10, 2 plus big O of n. Why did you say 2Tn by 2 plus big O of n? No. Okay. But twice. So let's go back here, no? Suppose, look at, I fix this case. I decided to pick him. I deleted this guy. Whatever may be the optimal solution here on this part, I could just compute this separately and compute this separately and put them together. Do you have any issue with that? Will there be a problem? I compute an optimum solution to this, compute an optimum solution to this. I don't see any issue, no? So basically, this is not this how the recurrence is actually. So I could replace this recurrence. Let's write down here less than or equal to. I could write down t n minus 2 n minus 2 divided by 2 maybe. Yeah. So if this is middle, so n by 2 minus 2 plus another same thing, right? And in another one, t of n by 2 minus 1 plus t of n by 2 minus 1. I could write like this, which is same as 4 times t of n by 4, sorry, n by 2 upper bounded by this plus some constant. I could write this, right? Because there are 2 vertices we removed. Fine. It's okay. Okay. And what does this also? What does this also? At least it solves to polynomial. Do you agree? This solves to polynomial? Are you sure that this solves to polynomial? Hmm? Hmm? It is like n square, no? Okay. So this is like order n square. Excellent. Polycan algorithm. Okay. So if I do divide and conquer, I could get order n square polynomial time algorithm if my input graph G is path divide and conquer, and I didn't have weights. Even then I could do divide and conquer. I mean, it's just simple, but even with weights I could do order n square time. But some people were talking about some dynamic programming, dynamic programming, dynamic programming. So now you have a choice to talk about your dynamic programming, dynamic programming. So what is a dynamic programming algorithm? Hmm? So how will I go about dynamic programming? What should I store at any vertex v? I should store some things, right? Hmm? I need to store some objects, right? So what are those objects? Huh? Is that enough? Is that enough? So he says to store AV is going to store okay, so first I'm going to by PV I will denote the path up to V ending it, okay. So AV for now stores max weight max stores max weight stores max weight independent set of PV up to PV. This is what it stores. Okay, how will you update AV? So suppose this is VI, this is what you store. Okay, so how, I mean, whenever we do dynamic programming, I need to write recurrence and prove that the recurrence is correct. So what is, how will I find AVI plus 1?
Weight of vi plus 1 plus avi or
Okay, so so all you are saying that this is nothing but max of either Vi plus goes into the solution, okay, fine. Then weight of Vi plus 1 plus AV minus 1.
I plus 1 you have taken, right? Yes.
Huh?
So up till vi you have to check.
You decide to pick.
Vi is not right. Okay, right.
And what?
And avi and api.
Okay, excellent. And how much time does this take? Order n time. All of you are amazing. Very good. Okay, so divide and conquer takes order n square, and this takes such a time. I just changed my graph. Okay. Now I don't have a graph, I have a tree. I do not have path, but my family of graph had changed to trees. And I want to get a polytime algorithm. Okay. So now I have trees. And I want to get polynomial time algorithm for max weight independent set or max independent set, doesn't matter, okay, on trees. Okay, so let's go back. For paths divide and conquer algorithm, what fact did you use? Conquer algorithm, what fact did you use? What did you use? Oh, removing Vi gave you two disjoint problem of roughly half the size. Okay? Crucial. What was the crucial thing to notice? Crucial. Removing a vertex okay, gave removing a vertex made two connected components, and hence I can do this of size roughly n by 2. This was the crucial, otherwise I would not have got my polynomial term. If it had given n minus 3 here and 3 here, then not sure that I could do anything. Okay, so this was crucial. Okay, and what was crucial for dynamic programming algorithm? What was crucial for dynamic programming algorithm? There was an ordering of vertices by which we could process the graph. Okay, so there was an ordering on sub problems. Okay, there was ordering. There was an ordering on vertices such that sub problems in some sense gets, like filtered, or I would say gets expanded. Okay, or there was a construction sequence, whatever that word means. There was a sequence by which we could construct the graph. And what was that? What did you do? Pi? How did you get Pi plus 1? You took Pi and concatenated Vi plus 1 to Pi, right? So this allowed you some way to do induction, right? And that was very crucial for your dynamic programming algorithm. I would like to make these two things also true for my trees. How am I going to achieve this? Do you get my point? So problem is clear, algorithm is clear, dynamic programming, I will leave it, but let me still, some gets, okay. So first of all, is it possible to actually get that? What? You can get connected component size exactly equal to n by 2. Patience.
But for some high degree vertex, it will delete it.
So
It may not. That could just we can. But even if it's very absolute and on top is
so let's make, what happens if we would have replaced this lemma? Removing a vertex, we had made two connected components. Removing a vertex results in every connected component of size at most n by 2. Is this helpful? If I would have this, will that help? Then my running time will be, notice, right? Either this vertex will go into the solution or this vertex will not go into the solution. Now my recurrence will be t of n is less than equal to 2 times, right? Roughly, right? Summation over t n I, ni is at most n over 2, right? And summation ni is equal to n, roughly like this. No? This is exactly what, right? I have to run twice on each of those components, right? So this is my running time of my algorithm. Do you know how to prove this is polynomial or not? Okay. This looks harder. Okay. If I wrote is this polynomial? Yes, no, maybe, could be. So this is basically 4 times t of n over 3. Sorry, what am I writing? In the worst case, this is definitely so what is this? I think n to the power maybe some 4 for sure. No? Like think of this way, right? I have n, I went to n by 3. And like in logarithmically, I'm going down and 4 and so something like that. So fine. This is poly. So what you could do that you have lots of components, just treat them as one, right? Group them together, treat them as one and remaining as one. So you can just have two subproblem. Call your MIS algorithm on this, MIS algorithm on this. That's perfectly fine. Just for your analysis, right? Just for you to understand. Otherwise, you get lots of terms and you do not know how to analyze it. Look, that itself also will give you polynomial. I mean, after all, you just don't understand why it is giving you polynomial yet. You know why it is giving you polynomial? Do you understand why it gives you polynomial? Because you first run your algorithm on one connected component, you have solved this, kept it, then you went to the another connected component, solved it, kept it, then you went to another connected component, solved it, kept it. So the running time is max of this times 4 or the number of connected component, that is why. Right? And the number of connected component is bounded by n, so this is some poly in n. So this is why this is. It's not product of the running time, it's a sum of the running time because you solve it, kept it separately, then you went to the other connected component, solved it, kept it, and so on and so forth. So first of all, there are two things. Here, in our problem on path, we could actually write 4 times t of n by 2. But it looks like that I could relax it and write n by 3 to n by 3 and I'm good. I could probably also write here 3n by 4 and 4 to the power 3n by 4 and still this will be polynomial. In fact, I could write any alpha n where alpha is a constant, suppose, and 1 minus alpha n and really, right, 2 times alpha n, 2 times 1 minus alpha n, and then I will get, suppose 1 minus alpha is more than alpha 4, right? Then I will get 4t 1 minus alpha times n, and you can show even this is polynomial. So you have that much of leeway all the time, right? So first of all, I do not have to be really balanced, but if I am eating a fraction of vertices each time, I will not go too far. I will very soon converge to a polynomial time algorithm, right? So having these thoughts in our head, now let's go back and try to replicate our success on path to success with trees. So there are two things, right? So by doing this, we learn two things. First of all, question number one. Does a tree T has a vertex such that every connected component has size at most Vt by 2. That's the first thing. And the question number two, let n1, n2, nl be set of integers such that summation ni equal to n and ni is at most n over 2, then we can partition n1, n2, nl into a and b such that mod a is at least some alpha, mod a is some alpha n, and mod b is at least some alpha n. Because if both are at least alpha n, then automatically you also have an upper bound on what a is, 1 minus alpha. Okay? So these two conditions. Because why I want this, if I'm able to prove this, I will get lots of bunch of connected components, right? I will get bunch of connected components, okay? Bunch of connected components, and I will treat each size as n1, n2, so these are my integers, right? Whose sum is at most n, and now because of this, their size is at most n by 2, and this will tell me that I can partition them into some connected components into A, some other connected component into B of proportionate size, and then I will run my algorithm on A and run my algorithm on B, so that it is easy for me to analyze. So this is the utility of this lemma, and this is an utility of a structural lemma. Okay. What should the vertex like V be called? First of all, let's give them name. First of all, after you delete V, graph has lots of components. So this is a separator, right? This vertex is a separator. So such a vertex will be called, okay, has a vertex. So this will be called separator. Okay, and we'll talk about what kind of separator it is later. Okay, so let's start to prove question 1 and question 2 first. Do you see a proof for this? How many of you have seen the proof for first? Have you seen the proof for this? Do you know a proof or do you know it exists? Okay. It's not rocket science. Okay. So here's my tree. Pick a vertex. Either this vertex is your desired vertex, either this vertex does the job for you, means if I delete it, every connected component out of this doesn't do a job. Why it is not doing a job to you? Because there exists a connected component whose size is V2 by 2, strictly greater than. Suppose this is that connected component. Then what is the size of this connected component? Strictly less than V2 by 2, right? Sum of all this. Okay. So I move my token. So root this tree at somewhere. Okay. I move my token to. I ask this guy, are you the right vertex? Because anyway, sum of all this guy. Yes. And so I move towards the mass. Okay. I ask this guy, does the job? Great for me. If it doesn't do the job, then everyone I go. It's a finite graph. So this step will stop in finite number of steps and you're done. Right? You can make it a proof as an induction proof or like induction on the depth or whatever. But this is a proof. I can keep in my head, you can also keep in your head. Just move the token towards the component which has the heaviest weight. And that's it. So this property holds. Excellent. Now let's prove this. Okay, so let's first prove this with alpha equal to 1/4. Okay, alpha equal to 1/4, and then we'll make alpha equal to 1/3. And then look, this is nothing to do with computer science. This is like some numbers. So what should you do? This much space is enough. So let's n1 less than equal to n2 less than equal to n3 and suppose without loss of generality. Okay. Look at the first time something goes beyond n by 4. Okay. It could be the first n1 itself. Let's call this A. Okay. First index such that first index I such that summation nj j going from 1 to I is more than n by 4. Right? It could be the first guy itself. Okay. So what you know, summation j equal to 1 to I minus 1 nj is strictly less than n by 4. You added ni to it. What is the weight of ni? N by 2, at most n by 2. So the sum here is at most 3n by 4. Okay. So this implies summation they at most 3n by 4. Agreed? So that's your partition. Okay. That's your partition. Okay. So this is a proof with 1/4, but we can do better. Okay, like 1/4, 3/4 partition. So like as much close these two numbers are, like half, that much better the running time of the algorithm will be. As much far they will be, that much running time it will So it is good to be as balanced as possible. Like these two sides should be as balanced to each other as possible in terms of size. Okay, so I'm using the word balance. Okay, okay. So how do we prove 1/3? Now I do slightly differently. Okay. Okay. N1 is greater than equal to N2, greater than equal to N3, dot 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 greater than equal to Nn. So I have done opposite now. Let this is highest. Okay. If N1 is greater than equal to N by 3, okay, then A equal to N1, B equal to N2 to NL. Because look, this is not more than half because this is singleton, right? So look, it is at least N by 3, but it is at most half. So this guy is at least 1/3. So I have proved 1/3, 1/3. And the upper bound on B is at most 2/3 because it could be equal. Okay. So you are not in this case. N1 is less than equal to N by less than What does it imply? Each ni is at most n over 3 because this was the largest. Now I apply the previous argument. Look at the first time, okay? Let I be the first index. Let I be the first index such that, let I be the first index such that j equal to 1 to I summation ni is greater than equal to n by 3. Okay. So before it was strictly less than n by 3. Every object has size at most n by 3. So this is less than equal to 2n by 3, and then you are done. Okay. And this is the best you can actually do. You cannot go forward. Okay. So we have proved both question 1 and question 2 for the trees. Like question 2 was just about this. So what will we do? I will apply this, group the components such that their size is at least 1/3. Both sides you are losing at least some fraction, and then I will apply inductively on them. So now my divide and conquer algorithm on trees will be what? If Vg equal to 2 or something, find max weight independence set. Now I cannot say Vn be the middle vertex. I will say let's look, it balances my graph into two parts right after doing. So these are called balance separator. Okay. Okay, I will define it later. Let Vn by 2 be the balanced separator. Okay. Now what will I do? I am not going to call, like, of course, so either this guy goes into the solution. If it goes, then I have to call my DCMIS on Gn by V2. That's still correct. Okay. It's just a running time that I could analyze. But algorithm wise, this is what I do. I just go compute, or I do this. Algorithm wise, I do nothing different. This is all that I do. Vn to the middle. That's it. I'm done. But the analysis now needs a little bit of tweaking, because how will I think about this? I will think about this because algorithm just goes on to each connected component and will run this out. But think of another way of thinking of this algorithm is that here is a vertex. I decided the state of this vertex. I solved left, I solved right. And what is left, right? I partition my connected component into A and B, partition the connected component to A and B, such that cardinality of A is at most n over 3 and 2n over 3. Same with cardinality of B is at most n over 3 or 2n over 3. So the running time of my algorithm will be, okay, running time of my algorithm will be T of n is less than equal to, actually I don't know, I know it is at least n over 3, right? So basically it is max of, you have to be very careful, right? Alpha between 1/3 and 2/3, right? T of alpha n plus T of 1 minus alpha n. This is it. I have actually no idea how did they got separated, but I have a guarantee that none of them is like the one guy is between alpha n and this, then the other guy is 1 minus alpha n. You can prove that then it actually happens, the worst happens at the end. Okay. So this is why people will write to 2t n over 3 plus 2t 2n over 3. Okay. And this is poly in n. Right. So this is my divide and conquer algorithm for my trees. What did I do? I picked up this vertex, got into my connected components, grouped them into A, grouped them into B, okay, solve my optimum solution here, solve my optimum solution here, like for those 4 sub problems, and based on those selection, those 4 sub solutions, I decided a solution for myself. That's all that I did. Okay, so this is divide and conquer. Now, how do I go to do dynamic programming over trees? Okay. Now I am going to probably drop this for a minute now. So we were talking about ordering of the vertices, right? Otherwise, how will I do? So tree also has a natural ordering, right? You root it at some vertex, then you have a leaf to root. Okay. Here is a tree, root at some vertex, say R. Okay. So I have rooted at this. So now I have root, right? So everything is this. Now for a given V, I can, what is TV? Vertex, sorry, tree rooted vertex V. Now AV stores the maximate independent set of TV. Can I do this now? When you had a path, you said, hey, look, if I pick him, then I don't pick him his neighborhood, which is same as go and look at the value here. Now what should I do? Where should I look his value? Why? Okay, excellent. Okay, so suppose I have V, it has a children, say for example V1, V2, V3, and V1 has children say V4, V5, V6, V7, V8, V9. What will you do for V? All you have stored is stores the maximum independent set of TV. Now give me a recurrence for TV.
Maximum of either V goes.
Okay, V goes into the solution, then what will happen?
If V goes, then look at the max weight of the subtrees rooted are its grandchildren.
Here.
Yeah.
Okay.
Or V does not go, then subtrees rooted are its children.
So either AB is weight of V plus summation AVJ, Vj is the grandchild of V, or V Wi say Wi is in neighborhood of V. Okay, is this correct? Yes, no, no. Why it is not correct?
Why we have to force that either all the children, like either this vertex will go, or all of its children will go in. We could have one of its children is going, and that will both vertex not to go.
No, I did not get it.
So here we are forcing either V is going, or V1 and V2 and V3 are going.
No, we are not forcing that. Where did we force that?
In AVI,
All it stores maximum weight independent set of TV. So whatever may be the independent set here, you take that independent set, you take that independent set here, take that independent set here. That their union is still an independent set.
Also, ABJ does not necessarily include the VJ, but it also includes the possibility that VJ
Abhishek, is it correct? Is the recurrence correct? Huh?
I can't say words.
Ran, is that correct? Seems correct. It is correct. Okay. What is the running time of this algorithm? Do you think it's correct? Or you still doubt it? I'm talking to you, Vaishali. Do you think it's wrong? Like, are you sure? Or again, you're using seems correct then? Huh. That's a. Okay. So, what's the running time of this algorithm?
It's again order n, right? Because you're just storing one n. It's order n into order n squared.
Order n square. Okay. So, when we did dynamic programming on path, you got linear time, and now you're getting order n square algorithm. No, I don't like it. So, can you do something to make it linear time? Hmm?
Two-dimensional dynamic. Just
Okay, so what should I do?
the state will have two states. So whether like store maximum weight independent set of TV which has V and which does not have V. So AV of 0 and AV of
Okay, wait. So you want AV should store maximum weight independent set of TV.
no, AV of 0 and AV of 1. So like
AV0,
store
AV1.
two integers.
Let's call it like V is the vertex, right? So give it two different, like here, change here. Why you are changing here? You get my point? Given this vertex, let AV store something. What is that? I will give you another guy, BV. Let him store something. I mean, I do not want to change the vertex because it is about this particular vertex. So what do you want to store here?
Stores maximum weight independent set of
T, B,
having V
having V in it. Okay.
and one which does not have V.
Does stores max weight independent set of TV that doesn't contain V. Am I right? This is what you said. Okay, so now give me the recurrence.
It's the same, so that will be
Huh?
you need to write
Huh? This is what you wrote, no? AB and BV. So now you have to tell me how to update it. This is just a definition you told me. So suppose I'm at a vertex V and he has a neighbor V1, V2, V3. So what should we do?
so it will be AV.
AV,
So it stores V. So it's summation of BA. No. Plus weight of V. So it's weight of V plus B of summation of
VI. Okay, I going from 1 to L. Children, not grandchild, their child. These are our child. Okay, this is AV.
yeah, and BV equals summation of max of AV and BV.
Max of
AV and BV.
what are we saying? What is BB?
Oh, so that's not containing V. So it's subtrate
Max of BV
V.
So what should be BB?
summation BV also.
No, because it can contain like one. Its subtree can contain its neighbor, or it may not contain its neighbor. No. So according to the definition, it's like max. Because its subtree is there, so it's not necessary that all its neighbors must be there.
There can be an independent set here in the subtree is maximum which does not contain.
Okay. Okay.
So that's I is equal to 1.
Okay, so at any point of time, I should take max of these guys. What if I was just wanted to, can I do this? Stores maximum bit independent set of TV. I forget this. And BV is that doesn't contain B. Can I still write recurrence? I don't insist on that it contains or doesn't contain. I just say.
Yeah, that means here it will be max of B.
So what is BV? Now, first let's compute BV. That doesn't contain V, right? So this is nothing but summation AVI, right? I going from 1 to L. Very nice. And what is AV?
AV is the same.
No, it can't be the same because now
It can't be the same.
may not be done.
It is.
AV may or
So
then it's
max.
max of this. You can write from BV. So you compute this first.
You have to first compute this, then compute this. Okay. So what's the running time of this?
Order of n time.
Why?
Order of it will be n minus 1 precisely because no for at each vertex. So if you consider like edge many computations are made. So how much you have only n minus. So it will be order of.
This is summation degree V. So why is this correct for after all? On picture it looks correct. I completely agree. I have absolutely no issue with. Why should I have any issue with algorithms people are proposing that? Do you know that you have to show it's correct?
For PP, how we generally prove is it has this optimal substructure property and it also has the overlapping subproblem property and you show.
How do you show 2 equal to 3? Oh, you can't show 2 equal to 3. Okay, fine. How do you show x is equal to y? Suppose in the maths, if you had two sets A and B and you had to show they're equal, what would you show? What would you do?
One is rectangle, the other is
Right? Excellent. So
So you can just say what if suppose she told was correct, then you can show that this set contains the graph. That's exactly what it does. So she was telling that is rate of B plus grandparent. So you know that B of E represents.
this is the current algorithm written. Either this is correct or this is not correct. If this is not correct, we should find fault with it, right? We all agree that this is correct. If this is correct, we should find a proof for it. And look, I'm not insisting that we find a proof for. I'm insisting because we need to find why it is correct. That why, I mean, it's not about our own mental test. We need to know why it is correct. And there is a reason why I can just write. Why can't I for any graph write all this? Right? So why does this algorithm only works for trees? Shouldn't we ask this question to ourselves? Right? And then we will understand, right, why we can generalize or not generalize, right? So I'm asking a very simple question. It is not about anything else, just that why is this correct? And to show, how do you show some recurrence is correct? If you write recurrence, how do you show it's correct? One is less than equal to other, right? Right? So it is not about DP, it's a recurrence, right? And if I have a recurrence, all I have to show that left hand side is less than equal to right hand side, and left hand side is greater than equal to right hand side, and then left hand side is equal to right hand side. Isn't this how we say? So if I have to show that x equal to y, what should I show? X is less than equal to y and x is greater than equal to y. This is exactly what I was trying to say. If I have to show 2 equal to 3, I have to show that 2 is greater than equal to 3 and 2 is less than equal to 3 and 2 is equal to 3. No magic. Excellent. So now let's go. No, like we have some meaning associated to this A, B, B, V, and so like let's zoom in, right? So AV stores a maximum weight independent set at V, right? And you wrote down that AV is equal to max of, right? And you are telling all these things up until now. You have been telling all these things, but there are reasons why this is true, and you must know why this is true, right? So let's zoom into this recurrence. You wrote weight of V plus what was AV? Weight of V summation. What did I write here? BVI. Okay. Summation BVI, VI, I going from 1 to L. Okay. And what was the other one? Was BV. Okay. So this is one recurrence, right? And another recurrence was for BV. What? Summation I going from 1 to L, A, VI. Okay. What is BV? It is a maximum weight independent set that contains, that is V. Okay. So here is my tree, right? Okay. So what are you saying? Okay, look at the independent set here. Look at the independent set. They are either contained here, 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 right? And what does AVI? The maximum weight independent set here. So clearly, it is computing maximum over all independent set here. In particular, that family of independent set over which my maximum is taken this part, right? It also contains this part, like it's like here, right? So what does it mean? This implies that so each of AVI could only be larger than this, may not be smaller than this. So this shows that VB is less than equal to this quantity. Okay. Now look at the independent set, which is, look at an independent, I have to now show the other way around, right? So this is where you are using something which you must understand. Okay, what is AVI? It is a maximum weight independent set in this part of the graph. It's a maximum weight independent set in this part of the graph, maximum weight independent set in this part of the graph, maximum weight independent set in this part of the graph. Let's call it I1, I2, IL. And what I would like to say? Well, I1 union I2 union IL is an independent set. How are you able to say this? Exactly. So, so I'm using something about trees to argue this.
So this is exactly what the optimum substructure property.
Structure property says. I do not even know and I do not even care what those optimal subs. I mean, I don't even know this name called optimal substructure. I know how to design algorithm, and I can argue about it without knowing. Okay, I am using crucially a property here that I could take their union, and what is my goal? This object is trying to take all maximum independent sets here. Look at the family of all independent sets here in this graph that do not contain V, and it is trying to find the maximum over this. Now I have given you maximum of all these guys and say, hey, their union is also independent set, and hence it belongs to this family here over which you are trying to maximize, and hence you have shown greater than or equal. But to do this, I use the fact there are no edges between them, right? So this is really a separator here, right? And please see that it is a separator there, and this is an important thing to see. It's a separator there. Everybody, all of you have seen tree width algorithms, and I'm sure you have read your books. But if I ask you to make DP, it will be you will have a hard time or difficulty over it. That is just because you do not understand what is underlying or the underpin of the things which works. It's better to understand that underpinning structure which makes it work, because then we see. Okay? So this is the reason why this. So I did not do this computation because, like, yes, all of you know how to do it. But what doesn't stick to your head is that I could take this union because they were separate connected components in itself, and it is nothing about trees. If I had some set of vertices and I had connected components here, right? So what if I had some subset of vertices here, some subset of vertices here, and I had lots of connected components here, okay? And I wanted to find an independent set, and I knew my intersection of independent set from here. If I knew my intersection of independent set from here, which is exactly what you said, either V is there or V is not there. So if I knew the independent set structure there, then I can then throw away, if I know this guy, throw away all the neighbors from here, just go solve here, take their union, and then that's perfectly fine, right? But if I want my algorithm to run very smoothly, right, because I delete one vertex, maybe they are unbalanced, this is like n by n minus 3 and 3, then this will be an exponential time algorithm, right? So not only I want an object to separate things properly, but in a balanced way. And why it is happening? Not always true. Think of this is that you are a human on this island and you are a human on this island, and this is only track of communication. How will you communicate? You can only communicate to this guy via this guy, right? This is exactly what is happening, right? So these objects forms a portal of communication, right? So now the point is, for any problem, how much information these people should pass on so that anything else outside is only able to make everything from this portal of information, right? Can I quantify this? For which classes of graphs can we quantify this? These are the set of questions that leads to our better understanding of the world, okay? So let's define the notion of, okay, all is well, okay? So now let me define the notion of balance separator, okay, for any graph G, okay? And then let's make a, okay, okay, definition. Okay. So I'm going to call a set of vertices balance separator. If I delete it, then every connected component has size at most half of the original vertices. Okay. There was another special property of these trees. Okay. What was the special property of tree? We proved that there is a vertex which is a balance separator. So what we proved? Theorem. Every tree has a balance separator of size at most 1. Look at any induced subgraph which is a tree, also has a balance separator of sizes, right? So if you look at, I mean, it's a basically it's a property which is hereditary, and we need this hereditary property. Why? Because when we recursively go, we would like to do the repeat the same, right? So if you like to repeat the same, I don't know what graph is going to come there. So I would like to define a notion about something which is like, oh, for anything I'm able to decompose into nice ways. Okay, and let's define. Let me define a new family of graph for you. Okay, I'm going to define a notion of, okay, t-decomposable graph. Okay, don't search internet, it will not, you will not find it. Don't look at FPT textbooks, either of them, you will not find any of these things. Okay, so if you read FPT textbook, there's a chapter on tree with certain perspective. You read kernelization book, there is also a chapter on tree with completely different perspective on purpose, because we were not confident which perspective is better to teach students. Okay, and I'm teaching you what I feel is the right way of perspective, which is neither that book or that book. It is just part of out of experience. Okay, so a graph G is t-decomposable if for every W subset of Vg, okay, the induced graph GW has a balanced separator of size at most t. Right? So this is my definition of t-decomposable graph. What is t-decomposable graph? A graph G is t-decomposable if for every W subset of Vg, if you look at the induced subgraph, I can break that, like I can come up with a balance separator of that induced subgraph of at size at most t. Okay? Okay? So let's call it zeta t is G is t-decomposable. Okay, and so zeta 1 contains all trees. Okay, okay, so let's stop here. Okay.